Okay, so very good morning to all of you. In the today's class, I want to share my knowledge with you about the RTL logic family, and DTL logic family, TTL logic family, and the Schottky TTL and the ECL logic families. Actually, I want to cover the topic of the bipolar junction type logic family, which consist of two types. One is saturated and another is non-saturated. So in the previous class, we already know the classification of the logic families. Mainly it is two types, that is bipolar and unipolar. Bipolar will be subdivided by the saturated and the non-saturated, and saturated will be converted or classified by the resistor transistor logic, that is called RTL, diode transistor logic, that is called DTL, and the transistor transistor logic, that is called TTL. And the non-saturated type of logic family will be classified as the Schottky type of TTL and the emitter couple logic, that is called ECL. In today's lecture, we will cover the bipolar type of logic family, that means RTL, DTL, TTL, and the ECL. So now I want to share the Is it visible?
Yes, sir.
Okay. So this is the classification which we already know. So we will cover it like a TTL, DTL, and TTL, the saturated type of logic families, these three, and the non-saturated, these two, Schottky, TTL, and the ECL in the today's lecture. So first, I want to cover the RTL logic family. In the RTL logic family, there is the basic components are the resistors and the transistors. Okay, it is a bipolar saturated device where the collector of the two transistors are connected with the driver resistance, that is with VCC. This is also called the passive pull-up transistors, because when these two transistors are in cutoff state, then the output will be logic high. So the resistor acts as a pull-up resistor. So this RTL, this is R and this is the transistors. For this reason, this is called the RTL, resistor transistor logic. This is a very popular because of its simplicity. The transistors are used here just like a switching device. It switches in on when the transistors are in saturation mode, and it switch off when it is in cutoff mode. Okay. So now the role of the base transistors, these two are, is to expand the very small transistor input voltage to the logical one, that means it's approximately 3.5 volt, because the input voltage range is the VBE range, that is 0.7 volt, which should be converted to the logic 1 level as the 3.5 volt by converting the input voltage into the current. This is the current controlling element, okay, R. the resistance is settled by a compromise. We should compromise the value of the resistance. It should be chosen as low enough to saturate the transistors in its saturation mode, and high enough, high value of the resistance should be chosen to obtain the high input resistance. Okay. The role of the collector transistor, collector resistor, is to convert the collector current into the voltage, and its resistance is chosen as high to saturate the transistors and low enough to obtain the low output resistance. Okay. If it is low output resistance, then the fan out of the RTL logic gate will be very high. So the consideration is that we should choose the low enough resistance to saturate the transistors at the base and the high enough base resistor to obtain the high input resistance. But for the collector resistance, it should be very high to saturate the transistors, and it should be very low to obtain the low output resistance to get the high fan out of the logic gate. Now the A and B are the two inputs, and the Y or the Q is as the output. Okay. So when the transistors are in saturation region, then what happens? These two transistors are on. Okay. So if these two transistors are on, then the maximum current should flow through the resistors R2, because it gets a path to the ground. Okay. Due to the low resistance of the two transistors T1 and T2. So the high current will flow through the transistors, through the resistors R2. Then the output at the Vy, that is called VCE is 0.2 volt for the silicon and 0.1 volt for the germanium. So for this reason, the output voltage will be low. So we will get logic 0 at the output. So when these two transistors are in on state or in saturation mode, then the maximum current will flow through the R2, and then all the voltage will be passed through the ground. So the output will be logic 0. Now when the transistors operate in cutoff region, so then there is no current will flow due to these two are off. So no current will be flowed because there is no path exist to the from the VCC to the ground. So there is no path is existing. So for this reason, the output voltage will be logic high, because the maximum voltage drop will occur at the R2. So we will get the maximum voltage just like there is no current, so there is 0 voltage drop will occur here. So then there is the maximum output voltage will be very much at VCC. So I repeat again, when these two are the saturation mode, then the maximum current will flow through the R2. So the maximum voltage drop occur in the R2. So the V out will be 0. Because this is the VCC minus I2 R2 is equal to V out. So if this is I2 is maximum, so then I2 R2 will be maximum. So VCC minus I2 R2 is approximately 0. So for this reason, the V out will be 0. Now if both these transistors are in cutoff mode, then there is no path exist from the VCC to ground. So there is no current will be produced. So for this reason, the output is as simple as the VCC, as the logic 1. So this is the basic operation of the RTL. The advantage of the RTL is The primary advantage of the RTL technology was that it used a minimum number of transistors, and in this circuit, using the discrete components before integrated the circuit, the transistors were the most expensive component to produce. So here we use the resistors and the transistors. This is very simple in design, but here we use the resistances. So for this reason, the noise margin is very low. The fan out is very pure. The propagation delay is very high due to this resistance, and the high power dissipation also occur due to the resistors R and R2. So there is the different configurations of the different types of gates in resistor transistor logic. This is the NOT gate. If A is equal to 0, then the transistors will not be in saturation mode. So it is in cutoff mode. So for this reason, no current will be flowing through the resistance R2. So for this reason, we will get Q as equal to logic 1 as VCC if it is not in saturation mode. So there is no path exist in between VCC and ground, so no current will be exist. So then the output will be as VCC. Okay. If this is 1, if this is A is 1, then what happens? Then the transistors will be in saturation mode. Then the maximum current will be exist, and it should be flown through the R2. So there is a voltage drop. So the Q will be is approximately at 0. That is called the logic 0. So this is the basic RTL NOT gate. Okay. Now if we want to design a AND gate, then what happens? If the both inputs A and B are the 0 volt or the logic 0, then it is not enough to turn on the gates of the both the transistors. This is the gate, collector, base, and the emitter. So this is the gate of the transistor. So if this is 0, so then these two transistors are in cutoff mode. Okay. So due to this, the VCC will not appear at the output Y or the Q. Okay. So the output will be grounded through the out R2. So then the output will be logic 0. Very simple. If this is 0, then this will be in cutoff. This will be in cutoff. No voltage drop occur at the output. So the output will be grounded through this resistor R2. So the output will be logic 0. Okay. Now if any one input will be logic high, then what happens? Suppose this is logic high. So this will be saturated. So this transistor will be on. But if this is 0, then this will off. Then what happens? So there is no connection in between VCC and output. So the output not reach to the VCC. So and also it is grounded through R2. So the output will be grounded to R2. So the output will be 0. So if anyone, because these two transistors are in series, so if any one of these transistors in cutoff mode, so then VCC will be open circuited to the output. So the output will be logic 0 due to the output will be grounded through R2. This is the simple operation. But when these two are 1 input, then what happens? This will be on, this will be on. So due to the input due to the low resistance of the transistors, the VCC will be at output. If both the inputs are high, then it will drive both the transistors will be turned on. Then the supply voltage to flow to the output through the transistors T1 and T2. Therefore, there will be the VCC in the terminal Q or the Y. But the output will not transfer to ground due to the high resistance of the R2 with respective to the resistance of the transistors. This is very high, this is very low. So the output will not be transferred to ground due to the high resistance of the R2. And the output is as the VCC. So the Q will be logic 1. Okay. Due to these two transistors are in series, if both the transistors will not be activated or in saturation mode, otherwise we will get the output as logic 0 due to this resistance R2. If both the transistors are in on or in saturation mode, then the VCC will transfer to the output, then the output will be at logic 1. So this is the basic AND operation. Now, if two transistors are in parallel mode, so then it will be converted as the OR gate. How? Now, if both the input as logic 0, both the input are logic 0, then these transistors are cut off, then these transistors is also cut off. So the output will transfer to the ground through this resistance R2. So then we will get the output as logic 0. Now if any one, suppose this is 1, this is 0, then what happens? This will be turned on, this will be turned off. Okay. So if this transistor is in turn on in saturation mode, then the VCC will transfer through this transistor to the output Q. So then the output will be logic 1. Okay. So now if this is 0, this is 1, then this will be in cutoff, this will be in saturation, then the VCC will transfer through these transistors to the output, then we will get also the logic 1. So this is the logic 1, this is the logic 1. Now both the input are in 1, then what happens? Then both the transistors are in saturation mode. So both are activated. So then also the VCC will be at output port Q. So the output will be logic 1. So this is the OR operation. So any AND operation, the transistors are in series. For any OR operation, the transistors are in parallel. Okay. So this is the basic simple operations of the RTL logic family. The example are given as the NOT gate, AND gate, and the OR gate. Now come to the NAND gate. The driving resistors are connected with the VCC. Before, for the OR gate, AND gate, and the NOT gate, the transistors are grounded. The resistance R2 are grounded. But here for any NAND operation, the driver resistance are connected with the VCC. This is the simple difference. Now if this is 0, 0, then what happens? These two are in cutoff, So no current will be produced through the R2 due to the open circuit. So the output will be as VCC. Okay. So now if any one of these are in saturation, then what happens? Also the open circuit exists. Suppose this is cut off, this is on. So this is the open circuit. So again the V out will be logic 1 because no current produced. If this is 1, this is 0. Then what happens? This will be turned on, this will be turned off. So again the open circuit exists. So there is no current. So the output is logic 1. Or if the both are logic 1, then what happens? Both are in saturation mode and also connected in series. So the maximum current will be produced through the R2 and the maximum voltage drop will be produced at the collector. Okay. So the output will be transferred to the ground through these two transistors. For this reason, the output will be 0 because VCC minus ICR2 is equal to V out. So if there is a maximum voltage drop occur due to the generation of the current, then the output will be logic 0. This is the basic operation of the NAND gate. Also the NOR gate, if these two are in parallel mode, so if both are 0, then both are cut off. So there is no current will be produced. So the output will be as VCC. Now if any one, suppose this is 0, this is 1, or this is 1, this is 0. Any one input is 1, then any one transistors T1 and T2, either T1 or T2 will be in saturation mode. So then we will get the connection in between VCC to ground. So the maximum current will be produced through this R2. So the maximum voltage drop will be exist at the R2. So the output will be 0. If this is any one of the input is logic 1 or the both the inputs are in logic 1. So if the transistors of either T1 or T2 or the both the transistors T1 and T2 will be in saturation mode, then the maximum current will be produced and the maximum voltage drop will be produced at the resistance R2. So there is no output voltage exists. So the output as logic 0. This is the basic operation of the different types of gate in the RTL logic family. So now come to the another type of logic family that is called the DTL. Where it is called the DTL? Why? Because here we use the diode and the transistor. So this is called the diode transistor logic. The merits of this type of logic family is easy to design or the manufacturing and the low power supply needed due to the low cutoff voltage of the diode. And the demerits are the lower speed of operations and the noise immunity will be very less. So there is some merits and demerits of the DTL. Now I come to the DTL logic family with some example. Suppose this is a NAND gate. This is a NAND gate that consists of two diodes DA and DB, and one transistor is Q1. The two diodes D1 and DA and DB and the resistor R1 as the input state, and the R2 and the Q1 is at the output stage. So the operation of this type of DTL NAND gate is when the two inputs A and B are 0. Then what happens? This is a PN junction diode. So this is P, this is N. Now the P side is connected with the VCC and the N side is connected with the ground or the logic 0. So this DA and DB are in forward biased. Is it? So if it is a forward bias, then the current will flow from the VCC through the R1, through the diode DA and DB to the ground. Okay. So there is a maximum drop exists at the R1. So there is no current will be produced through the R2. So there is no voltage drop due to, if there is a current flow through the R1 and DA and D2, so there is no voltage drop exists at this point at the base of the transistor Q1. So Q1 are in cutoff mode. So if Q1 is in cutoff mode, so then it is open circuited. For this reason, there is no current will be produced through the R2. So the output will be as VCC. For this reason, it is called logic 1. So now I repeat again. If these two diodes are in parallelly connected, if any one of the input or the both the inputs are in logic 0, then the diodes DA or the DB or the both of the diodes DA and DB are in forward biased. For this reason, the current will be flown through this resistance R1. So no current will be produced through R2 due to the cutoff condition of the Q1. So the output will be at logic 1. Now, if the both the inputs are in logic 1, both the inputs are in logic 1, then what happens? Then both the diodes are in cutoff. So the voltage drop occurs at the base region of the Q1. So the current will flow through this R1 through the transistors to the ground. So any one of the diode are in cutoff region. Sorry, both the diodes are in cutoff region due to the both the inputs A and B are in high. Then the diodes are in reverse bias. So the both the diodes will not be conducted. In this case, the voltage from the supply VCC will be enough to drive the transistors Q1 in the conduction mode or the saturation mode. Then the transistor will conduct through the collector and the emitter. Collector to the emitter. So there is no voltage drop. Sorry, there is the high voltage drop occur at the output R2. So the VCC minus ICR2 is equal to 0 as the output. Clear? So if both the diodes are in reverse bias, then the current will flow through this R1 and this voltage drop will be greater than the VBE 0.7 volt. Then the transistors will be in saturation mode. If the transistors will be in saturation mode, then the current will flow through this R2 to the ground. Then the voltage drop will occur at the output resistance R2. So then there will be no voltage at the output. So the voltage, so the output at the Y treated as the logic 0. So this is the NAND gate. So now if this is 0, 0, then the diodes are in forward bias, then the current will be flow through this. So there is no current will be flown through this R2. So the output will be the VCC. So the output will be at logic 1. If any one of these will be turned on, 0, 1 or 1, 0, then also the same occurrence will be occurred. So there will be no current flow through this R2. So then we will get the Y equal to VCC. So for 0, 0, we will get 1. For 0, 1, A and B and Y, that will be also 1. Either 0, 1, then will be also 1. If it is 1, 1, then the diodes will be in reverse bias. Then the current will not flow through this. The current will be flown like this. So the voltage drop occur at the R1. That will drive the transistors Q1 in saturation mode. Then the path will be exist from VCC to ground. The current will be produced. Then the voltage drop will be generated at the R2. Then the output will be logic 0. So this is the basic 2-input DTL NAND gate. For the NOR gate also, these two diodes, if this is 0, 0, if this is 0, 0, then what happens? So then that will be in reverse biased. Okay. So if it is reverse biased, then there is no current. So there is no voltage drop exist here. So the transistors will be in cutoff. So the diode, the LED output is the forward biased. So this is on. So for 0, 0, this will be on. If any one of the 0 exists here, or the any one is exist here, or the any one diode is in forward biased, then what happens? Then the current will be flown through this base resistance and the voltage drop will occur and it will drive the transistors TR1. Then what happens? The current will be produced through this. So the voltage drop will be occurred here. So the output will be 0. Then the LED will be in reverse bias. So there is the output will be 0. Similarly for this, drive these transistors 1, then the current will be flow like this, then the output will be 0. If both the 1, then also the transistors will be in saturation, the current will be flown like this. So then the output will be as logic 0 for the 2-input DTL NOR gate. Okay. So till now it is okay, or if there is any question? Hello?
Sir, up till now understood.
Okay. So now I will go to the next type of logic family that is very much important, that is called the TTL logic family, transistor logic family. It consists of the transistors at both the input and the output stage. In the previous stage, we see that either diode or the resistance are in the input stage, and the output stage will be the transistors. Now here in the TTL, the input and the output, both the stages are consisting with the transistors. Unlike the resistor transistor logic, that is, or the DTL logic, here both the logic function and the amplifying function are performed by the transistors. In the RTL or the DTL, the output transistors just act like a logic function. But here the output transistors also amplify the output. Okay. So in the TTL integrated circuits, it is very popular in the different applications, including the computer controls, consumer electronics, or in the industrial control systems, etc. And most of the ICs, the 7-port series ICs, are manufactured in this type of logic family. Okay, so there are various sub-families also there. I already discussed in the previous lecture. That is the standard TTL, low power TTL, Schottky TTL, advanced Schottky TTL, high power TTL, fast TTL, very fast TTL, etc. So the difference is only that here the input transistors have the two emitters. This is called the two emitter transistor. And this transistors is just like this configuration. This is the base emitter junction. This is also the base emitter junction. This is P and this is N. This is P and this is N. So here these two input leads, emitter leads, acts as a diode in parallel configuration. This is a PN diode also. 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 Okay, this is nothing but a two emitter transistors, is nothing but this configuration. Okay, and this configuration, that is the P and N, and this is the P and N. Okay, so this is the P and N. This collector junction acts like a third type of diode, that is called DC. So these transistors is configured with the 3 diode model. This is the DA, this is the DB, and also this is the DC. Okay. So if you understand this configuration, then the total TTL logic operations will be very easier. This is the base emitter junction, PN junction diode. This is the base emitter junction, PN junction diode are connected in parallel. And this is the PN junction diode, which is connected in series with the PN junction diode of the output transistors. So now there is some advantages of the TTL family. The TTL family is very fastest saturation logic family. Typical supply voltage is only the 5 volt with a permitted variation is plus minus 0.25 volt. So at present the TTL gates are 3 volt and even the 1.5 volt supply voltage are possible. It has good noise immunity. That noise margin is approximately 0.4 volt. The power dissipation is in the range of the several milliwatt only. In the case of low power Schottky TTL gates, this is less than 2 milliwatt per gate. So it is very low. So the TTL gates are compatible with the other logic families. The commercial and the military versions of the TTL gates are available. These gates are more freely available in the open market than the most other logic families. It has the good fan out. It can drive up to 10 gates by a single gate. So this is the fan out. This is very much important. The TTL gate, the maximum fan out will be the 10 gates, 10. So the TTL gates producing almost all the logic functions are available in the market. TTL gates exhibit low output impedance for the high or the low states. These are the advantages. But there is some disadvantages also there. The noise immunity is not very high. So the TTL gates cannot be used in applications where the large noise voltage exists. Because of the isolation problems which require more cheap space, the TTL VLSI circuits are not possible in its conventional form. The VLSI circuits will not be made by the TTL logic families. This will be made by the CMOS logic families. We will discuss in the next class. So the power dissipation of the TTL gate is much higher than the NMOS gates. The cost of the TTL gates is higher than the NMOS or the CMOS when the MSI and the LSI gates are considered. The TTL gates generate the transient voltage at the switching instant. The wire or capability is not possible for the conventional TTL gates, which are possible in the RTL. Now come to the some examples of the TTL NAND gate. The TTL inputs are the emitters of the bipolar transistors, already told in the previous slide. The DA and DB represent the two input emitter junction, and the DC represents the collector base junction of the Q2. Collector base junction of the Q2, as well as the collector base junction of the Q1 also. So now the operation. When all the inputs are held at high voltage, this is high. So that means this is 1 and this is 1. So both the diode DA and DB are in cutoff or the reverse saturation mode, reverse mode. Okay. So that means there will be, then what happens? These two diodes are not conducting. So the current will be flow through this. So the diode will be in forward bias and it will drive the output transistor Q2 in saturation. So if this is in saturation mode, then the current will be flown like this. So the output will be logic 0. So if these are to 1, then the output will be logic 0. So this is the NAND gate. If any one of the one, then what happens? If this is 1, if this is 0. Now if this is 0, both are in parallel, two diodes, DA and DB. Then what happens? Due to the low resistance of this, the current will be flow like this. So this diode is in reverse bias, DC. So the Q2 will not be operated or will be in cutoff state. So there will be no current will be flown through the R2. So the output will be at logic 1 because there is no current will be produced through the R2. Okay, so the output will be as VCC. So this is the logic 1. So if either this is 0 and 1, then it will be logic 1. Either this will be 1 and 0, then also it will be logic 1. If now this will be 0, 0, then also both the diode are in forward biased. This is 0, this is 0. So both the diode are in forward bias. So the current will be flown through this diode to the ground. So this diode will be in reverse bias. So there is no voltage drop occur at the base of the transistors Q2. So the Q2 will be in cutoff. So there is no current will be produced through R2. So the output will be logic 1. So this is the NAND gate operation. So now if the, here I also described the an input of the logical is 0. Note that the base collector junction of the multiple emitter transistors and the base emitter junction of the output transistors are in series between the bottom of the transistors and the ground. So if one input voltage becomes 0, the corresponding base emitter junction of the multiple emitter transistors is in parallel with these two junctions. So the phenomenon called the current steering means when the two voltage stable element, that means two diode with different threshold voltage are connected in parallel, then the current flows through the path with the smaller threshold voltage. That is, the current flows out of this input and into the 0 voltage source. So as a result, no current will be flows through the base of the output transistors. Okay. So it stops conducting because DC will be in reverse bias. So there is no current will be produced. So the Q2 will be stop conducting and the output voltage will be logic high. This is the basic operation. Now, this output state have the three configurations of the TTL logic family. One is called the totem pole output configuration. Another is called the open collector. In the digital circuit lab, there is the two types of NOT gates are there. You already know. Otonu sir already told you. That is the open collector type. Another is the totem pole. So these are the two configurations. And another configurations are there that is called tri-state. So there is three output configurations exist in the TTL logic family. First, I want to describe the two input TTL NAND gate with the totem pole output. This is the totem pole output configuration. At this output, this configuration will be attached. Here the four transistors Q1, Q2, Q3 and Q4. The Q1 has the two input as earlier, two emitter that is A and B, and Q3 and Q4 and a diode that is called and one. What is the operation of the diode? I will come to the next slide. This resistance R4 is called the current limiting transistors because it limits the current. Okay, and this configuration is called the totem pole configuration. One current limiting resistor 2 transistors and 1 diode. This configuration is called the totem pole configuration, which is attached at the output of the TTL logic family. Now, in this arrangement, a driver transistor provides the complementary voltage. This is the driver transistor Q2. It provides the complementary voltage for the 2 output transistors Q3 and the Q4. The either Q3 or the Q4 conducts depending upon the complementary logic status of the input. The diode D ensures that the Q4 is able to turn off rapidly for the high switching when it is required. So the diode will confirm or will ensure that this output transistor Q4 will be rapidly turned off or not for the fast switching purposes. The advantage of this type of configuration is it had the low power consumption, fast switching, and the low output impedance. So these three are the advantage of the totem pole configuration. Now the operation. Now if both the inputs A and B are low, these two are low, then what happens? The current due to the supply voltage VCC will go to the ground, through the R1 and the diode DA and DB due to the diode DA and DB are in forward bias. This is 0 grounded. So P are N is grounded, P is connected to VCC, P is connected to VCC. So the current will be flows like this. When both the diode are in forward biased or the input as logic 0. So then what happens? The supply voltage gets dropped in the resistance R1. So it will not be sufficient to turn on the transistors Q2 because the voltage drop at the R1 exists. So the DC, the current will be flown like this. So the DC will be in cut-off state or the reverse bias. So there is no driving voltage exist to drive the Q2. So if the Q2 is turned off or the open, then what happens? The Q4 also cut off. If this is open circuited, then this also the open circuited. So the Q4 are in cut off. So if Q4 is cut off, so the current will be transferred through the R4 due to the Q3 is turned on, because this voltage drop will drive the transistors Q3. So VB voltage is greater than the 0.7 volt. So this is the turn on. So the current will be flows like this. Okay. So the Q3 is in the emitter follower circuit. So the output terminal will be as logic high. Okay. I repeat again. If both the output input is logic 0, then the DA and DB are in forward bias. So the current will be flown through the 1 to the DA and DB to the ground. So there is no enough voltage occur to drive the transistors Q2. So the Q2 is open circuited. So the Q4 is also the open circuited. So due to the emitter follower transistors of the Q3, the voltage at the output is logic 1. This is the simple operation. Now, if any one input is logic 0, suppose this is 0, this is 1, same operation will be exist. So the Q4 will be cut off. So the Q3 is pulled high. So the output will be at logic 1. So when this is 0, 0, then we will get the output as logic 1. When this is 0, 1, then also we will get the logic 1. When this is 1, 0, the same operation will be done. Now when this is 1, 1, then what happens? Then this DA and DB are in reverse bias. So the diode DC will be in forward bias. The current will be flows like this. The diode will be DC will be in forward biased. So then what happens? The transistors Q2 will be turned on or in saturation, and it will drive the transistor Q4. So now if the transistors Q4 is on, then there is a current path exists. So the output will be logic 0. Okay, clear? So if this is 1, 1, then the output will be logic 0. So this is an AND gate. Okay. So this is the NAND gate of the totem pole configuration. Now the another configuration is called the open collector output. You see that in the open collector output, we just eliminate this portion here, and the one pull-up resistor is connected with the VCC and the output. Additionally, we remove the R4, Q3 and the diode and connect the pull-up resistor with the VCC to the output. This is the open collector configuration. The output is taken from the open collector terminal Q4. When the transistor Q4 is off, then there is no current will be produced from VCC to ground. So the output will be VCC. So as logic 1. And when Q4 is on, then the output will be 0. So now if this is 0, 0, the input, then what happens? The current will be flow through this. So the Q2 will be off. So if Q2 will be off, then Q4 will be off. So we will get logic 1. So if this is 0, 1, so any one of the diode DA and DB will be turn on, then the current will be flown either DA or DB. So the Q2 will be off. So if Q2 will be off, then Q4 will be off. So the Y will be 1. Now if it is 1, 1, Then the two diode DA and DB are in reverse bias. So the current will be flown like this to drive the transistors Q2, and then the Q2 will turn on the Q4. So there is a path in between the R4 and the RL and the Q4. So there will be the output will be 0. So this is the open collector type configuration of the TTL NAND gate. Now come to the third state, that is the tri-state gate. While operating the transistors in this output configuration, it is possible to attain the high speed. Three output state is possible here, that is high, low, and the high impedance state. When the Q3 is on, this is the totem pole configuration. Okay. So when the Q3 is on, the output Y is high. When the output is low, when the Q4 is on, as before. But in the third state, when both the transistors Q3 and Q4 are on, by the controlling input of the diode D1, then we will get the output is neither low nor high. It will be in high impedance state. Okay. So if this is on, this is off, then the output will be 1. When this is off, this is on, the output will be 0. Now when both this will be on and this will be on by the controlling input of the diode D1, then we will get the high impedance state. Okay. So this is called the tri-state. So these are the all three combinations, output combinations of the normal TTL logic family. Now we come to these are all the saturated transistors. Okay. So now if I come to the non-saturated logic family, these are divided in two types. One is Schottky TTL, another is ECL. Now let us know what is the Schottky TTL. The Schottky transistor is nothing but a conventional bipolar transistors with a Schottky diode connected in between the base and the collector of the transistors. So Schottky transistors is nothing but a combination of a normal NPN transistors with a Schottky diode, PN junction diode, no, this is the Schottky diode, and which is connected to the base and the collector junction of the normal NPN transistors. This is called the NPN Schottky transistors. Okay. The Schottky diode has the lower forward bias, that is 0.25 volt. When the base emitter junction would become the forward biased, then the Schottky diode bypass the current, preventing the transistors from going into the saturation. When this is on, then it bypass the current to prevent the transistors in saturation mode. The Schottky diode clamp prevents the transistors from going to the deep into the saturation. It reduces the transistor switching time, reduces the propagation delay. Power delay product is not reduced due to the lower resistance is used here. So this is very much important. The propagation delay is reduced, okay, but the power delay product is not reduced due to the lower resistance is used. The low power version of the Schottky TTL has the power delay product is 4 picojoule. Okay. So now come to the operation of the Schottky TTL NAND gate. The Schottky clamped transistors are used to construct the Schottky TTL NAND gate. Here, this is a Schottky TTL, this is a Schottky TTL, this is the Schottky TTL, and this is the Schottky TTL. But at the output stage, the transistors Q4 and Q5 are attached in series, but there is no diode exist. Okay. So the diode, Schottky diode D1 and D2 are the clamping diodes for the protection against the negative input voltage. That is the negative surge current actually. Okay. To damage the Q1. It will prevent the damage of the Q1 from the negative surge current. These diode D1 and D2. These are the clamping diodes. Okay. But here there is no diode exist. So the transistors Q3 and the Q6, this is the Q3 and the Q6 are included additionally. If any one or the both the inputs of the transistors Q1 is low, low means this is the, suppose this is low, this is low. So low means there is a diode. Okay. So the Q1 will be on. Low means this is a forward bias. The diodes DA and DB are forward bias. So the transistors Q1 will be on. So the Q2 will be off because the current will flow like this, from like this. So the Q2 will be off. If Q2 will be off, then Q3 and Q4. If the Q2 will be off, then Q3 and the Q4 will be on. If this is off, so then there is no current. Okay. So this node voltage is the VCC. So it will drive these transistors as well as this transistor. I repeat again. If this Q1 will be turned on, then the current will be flown through this R1 and the diode DA and DB to the ground. So there is no voltage drop exist at the base emitter junction of the Q2. So the Q2 will be turned off. So if this Q2 will be turned off, so then there will be no current will be produced through R2. So the base, at the base of the Q3, the voltage will be VCC, which will drive the transistor Q3 as well as the Q4. Okay. So as the Q3 and Q4 will be on and the Q5 and Q6 will be off due to the off of the Q2, then the output will be logic high due to this, and this will be on. Q3 and Q4 will be on, so the output will be 1. So now if A and B will be 0, then the output will be 1. Now if any one of the voltage, any one of the input of this Q1 will be 0, either this is 0, 1 or this is 1, 0. the similar operation will be done. So that will be also one output. Now, if both the inputs are, both the inputs are 1, 1. If both the inputs are 1, 1, then what happens? That DA and DB will be in reverse bias. So the current will flow like this, and this, and this. So then the Q2 will be turned on. It will drive the transistor Q5 and Q6, and the Q3 and Q4 will be in cutoff. So as the Q5 and Q6 will be turned on, then the output will be grounded. So the output will be logic 0. Clear? So if both the input are logic 1, then the DA and DB two diodes are in reverse bias. So there will be no current will be flown through this. So the current will be flows through R1 to the Q2. So the Q2 will be drive on, as well as the Q6 and Q5 will be drive on or in saturation mode. So then the output will be transferred to ground through the Q5. So the output will be logic 0. So this is the basic operation of the Schottky TTL NAND gate. So these are the TTL family, the 7-4 series, the bipolar, saturated, then come to the 7-4S series, then come to the 7-4LS series. From the 7-4S series, we get the 7-4AS series, and from the 7-4LS series, we get the 7-4ALS series, and finally we get the 7-4F series very fast. Okay. Now these are the widely used 7-4 series of ICs, and here these are not used at that moment. So now come to the last type of saturated logic family, bipolar saturated logic family, that is the ECL logic family, that is emitter coupled logic family. The emitter coupled logic is the fastest of all the digital logic families. Mind it. This is the very much fastest logic families, ECL. Okay. It is a very good MCQ questions in any competitive exams. Which logic family have the highest speed? That is the ECL, emitter coupled logic family. It was invented by Hanon Siot in the year 1956 at IBM. It is also called the current mode logic. Okay, so these are the current source. Already you know in the analog electronics subject. The design of the ECL circuit consists of the transistors and the resistors. By preventing the resistor from the entering in the saturation, the high speed operation is achieved in the ECL logic family. Very small voltage swing is necessary to switch in between the two different voltage levels, the high level and the low level. So this cannot be achieved in the transistor logic. Okay. So transistors enters into the saturation mode while in the operation. So there is a very low time needed or very low switching voltage needed to switch over from the saturation to the cutoff in this logic family. The emitter coupled logic family offers an incredible propagation delay of 1 nanosecond. Very fast. The delay is more reduced in the latest ECL logic families. In this section, we will describe the OR and NOR gate ECL logic, in ECL logic. There is some advantages, that is high speed operation, It reduces the shortage of the delay. Fan out capability is very high, and as well as it has some disadvantages, that is the low and high logic levels are kept close, so it reduces the noise margin. It not allowed to enter into the saturation, so the power consumption is very high. So advantage is power consumption, disadvantage is power consumption is very high, and the low noise margin due to the voltage level are very less. Okay. So now come to the example. The inverter circuit of the emitter coupled logic. It has two NPN transistors which are emitter coupled with the emitter resistance RE to the VEE. There is a single-ended input mode, differential single-ended input mode. When this is low, so that will be when the input is at Q1 is high, then the output here we will get two outputs. Then the output will be low at that output, and here at that output the output will be high. I will come to the later section. Both the emitters are connected together with the common resistance RE, which I already told. It is a current limiting resistance used to prevent the transistors from entering into the saturation. It has two outputs, that is out 1 and the out 2. There is the inverting input output is out 1, this, and this is the non-inverting output as out 2. The V in is the input terminal where the low or high input is given. This is the V in. On the other side, when the input V in is given low, then these transistors will be in cutoff. If this is 0, then the transistors will be in cutoff state. And the transistors, another transistor, if this is cutoff, then the Q2 will not enter into the saturation. Please note it down. On the other side, when the input V in is given low, it will turn off the transistors Q1 and the transistors Q2 will be turned on. It should be Q2. So this will be turned on because this is ground, this is at V always 1. Okay. So it will make the output V out 1 to be pulled high because this is cut off. So there is no current will be produced. No current will be produced from VCC to BE. So we will get at the output V out 1 at VCC. Okay. But this is turn on. Then what happens? The output will be at low value. This is turn on, V0. So this is turn on. So due to this, the current will be flow like this. Like this. So the output will be 0. So the V out 1 will be 1 and this V out 2 will be 0. So when the input is V in is high, then the Q1 will be turned on. So the current will be produced like this. Okay. So the V out will be 0. So at V out will be 0. So then what happens? This will be in cutoff. So then this will be as logic 1. So when the V out is 1, then the V out 2 will be 0, non-inverting. When the V out is 1, then the V out 2 will be 0. So when the V in is 0, then the V out 1 is 1 as the inverter, and it will be 0 as the non-inverting output as a buffer. When it is 1, then Q1 will be turned on, then the V out 1 will be 0. Similarly, for the V out 2 will be 1 due to the emitter coupled logic of the Q2. So Q2 will be turned off. It will be in non-saturation mode because this R1 limits the current to the Q2 into the saturation. Go to the saturation from the cutoff. This R1 limits the current to go to the saturation mode of the transistor's Q2. So for this reason, this is in off state. So then the output will be logic 1. Okay, clear? Due to the emitter coupled logic. When this will be on, this will be off. When this will be off, this will be on. Due to the emitter coupled logic and the current limiting transistors RE. It will prevent one transistor go into their saturation mode. Okay. When it will be in saturation, then it will prevent Q2 to go to the saturation. When Q2 in saturation, then it will prevent go to the Q1 in saturation. So for this reason, we will get the inverting and the non-inverting output. Okay. Now if we come to an example of a NOR gate. Here this is VBB is connected. Here this is V in 1 and the V in 2. If the two transistors are connected in parallel, then we will get the NOR operation. Okay. These two are in parallel configuration. If we connect these two in series operation, series connection, then we will get the NAND operation. Mind it. Then we will get AND and NAND. Okay. So if the transistors are in parallel, then we will get the OR operation or the NOR operation. If the transistors are connected in series, input transistors are connected in series, then we will get the NAND operation and the AND operation. Okay. So here I give the example of OR and NOR. The homework will be the NAND and AND. Okay. Please write the operation of the NAND and AND emitter coupled logic and send it to me through the WhatsApp. Okay. So now come to the emitter coupled OR and NOR operation. It is the slight modification of the inverter circuit. The one transistors additionally attached as parallel or connected as parallel. When the inputs at both the transistors Q1 and Q2 are low, both the transistors are low, then both the diode of the base transistors, emitter transistors are in forward biased. Sorry, reverse biased. When the both are the low, then the PN junction P is connected with low. So the diode of the two transistors, base emitter junction transistors, are in forward bias noise, reverse biased. Okay. So if the diode are in reverse bias, base emitter junction diode is reverse bias, so the Q1 or Q2 are not connected or not in saturation. So for this reason, we will get V out at logic 1. Okay. When one of the input V1 and V2 are logic 0, suppose if both are 0, then the Q1 or Q2 are not in saturation. So then we will get the output V out 1 as logic 1. So now if this is 1, this is 0. Then what happens? Then we will get the Q1 or the Q2 are in saturation. When this is 1, 0, then the Q2 will be in saturation. So then we will get the output as logic 0. If this is 0, this is 1, then this will be are in saturation. So the current will be flow like this, like this. Okay. So the output will be logic 0. When both the 1, then both the transistors Q1 and Q2 are turned on, then we will get the output as logic 0. Similarly, this is the non-inverting. So obviously we will get 0, 1, 1, 1 due to the emitter couple logic or the current limiting resistors RE. Okay. So if these two are in saturation, then it is in cutoff. When these two are in cutoff, then the Q3 will be in saturation due to the emitter couple logic. For this reason, we will get the two outputs, inverting outputs and the non-inverting outputs. This is very easy. Okay. So then we will get the NOR as like this as the V output 1, and as well as the OR output that will be the 0, 1, 1, 1. Okay. So this is the ECL logic family. All the operations are described here. I already told. So these are the references from where I make the lecture. So if have you any question, please ask me. Is there any question? Hello?
No, sir.